So welcome to our last topic for mechanics for this year, circular motion, part of the NCA Level 2 Physics course. Okay, so here's an example of the application of this topic. Centripetal forces keep these children moving in a circular path, and we're going to investigate that further as we move through these slides today. Okay, speed. So let's look at an introduction. So one rotation is once around a complete circle. The distance of a circle, of course, is 2 pi r. So therefore, and the time taken for one rotation will be the period capital T. And we're going to also link that to frequency, where frequency is related to period, where the period is 1 over the frequency, the reciprocal. And the velocity, therefore, will be distance over time. So distance in the case of circles is 2 pi r. So velocity will be 2 pi r divided by the period it takes to go round once. And here's this illustrated in a diagram. So you have a ball, for instance, being hurled around, has a speed. So the speed will be the number of evolutions times the circumference divided by the time it takes for those revolutions to occur. So uniform circular motion. So uniform circular motion is the motion along a circular path in which there is no change in speed. Speed in circular motion is a constant. Okay? The only change is in direction. Okay? So velocity changes because, of course, velocity has a direction component, but the speed of the ball does not change. So the constant velocity is at right angles to the path of the ball. And a constant force acts towards the center of the rotation, or the circular motion. Okay, so my question to you is there an outward force on the ball? Okay, so just pause the video now and have a little think about that, and we'll get back to you. Right. So the question of the outward force can be resolved when asking what happens when the string breaks. So if there was an outward force, the forces would be unbalanced and it would then shoot out the ball. But if there is no outward force, it will continue on as a right angle or a tangent to the direction of the acceleration. So you can see when it breaks, it goes off at a right angle rather than out. So it means there's no outward force. The ball does not move with a tangent to the path or at right angles to the path, not outward as expected. So this means that the centripetal force is removed. The ball continues in a straight line. So the centripetal force is needed to change this direction. And now we're going to go on and investigate this centripetal force. Okay, so here's some examples of centripetal force. So you're in a car, you're sitting in the seat next to the outside door. So what direction of the resultant force is there as you turn into a corner? Is it away from the center or towards the center of the turn? So essentially, are you leaning into the turn or are you leaning out? The car goes around the curve. The force on you is towards the center. So the car example continued. So here's you sitting in your car. The centripetal force is exerted by the door on you. Okay, so it means it's going that direction. There we go. There is an outward force, but it does not act on you. It is a reaction force exerted by you on the door. Okay, it affects only the door. Here we go. of the man. And the final example, a spin cycle on a washer. How is the water removed from clothes during a spin cycle of a washer? Well, think carefully before answering. Does the centripetal force throw water off the clothes? Yes or no? Quite clearly not. Actually, it's a lack of force that allows the water to leave the clothes through holes in the circular wall of the rotating washer. So let's look at the centripetal force in more detail. So consider a ball moving at constant speed v in a horizontal circle of a radius r at the end of a string tied to a peg on the center table. So assuming there's no friction. So here we have it here. So you've got a radius r and a kind of velocity v here, constant. So there'd be a tension force acting towards the center, okay, tension force T, and there would be a weight force, of course, acting, and a normal force acting. So quite clearly there's no movement of the ball up and down, so the weight force must equal the normal force. So what is this mystery tension force? Let's move on. We must derive its equation. Okay, so when a ball on a string is whirling in a circle, various forces are acting, as we've seen in the last slide, and there's a tension in the string which pulls the ball inward. Okay, the direction of this force is at right angles to the ball's motion. This force changes the ball's direction because the forces are always at right angles to the direction of the ball's motion, the speed of the ball does not change. This is important. Okay, so the force on the ball provided by the tension in the string is called the centripetal force. Okay, so another name for this is your centripetal force. Okay, centripetal force. It causes the ball to accelerate because obviously it's an unbalanced force by changing the ball's direction, but not its speed. Okay, so that's your velocity. Your change in velocity occurs because you've got a change in direction, not a change in the magnitude of that direction. Okay, but the ball is continually accelerating in the direction of the centripetal force, in this case towards the center, right? So that's where the ball's trying to accelerate to. Okay, and this acceleration is called the centripetal acceleration. So if v is the speed of the ball in meters per second, and r is the radius of the circle in meters, then the centripetal acceleration will be given by the following formula, which I've illustrated here. The acceleration equals the v squared divided by r. Okay, so from Newton's second law, force equals mass times acceleration. A bit of a tongue twister there. Okay, you can then derive the equation force equals mv squared divided by r. Now, how do we do this? Well, it's quite simple, really. Okay, so you've got this part here, of course, is your acceleration, right? So if force equals mass times acceleration, then it's going to be mass times v squared divided by r divided by, oh, yeah, there you go. Yeah, sorry. It's going to be force equals mass times v squared divided by r. Because remember, acceleration equals v squared divided by r. So once you substitute it in, force equals mv squared divided by r. Okay, quite straightforward. Okay, so this means if it has a mass of m, the centripetal acceleration and force will be given by the two equations, the acceleration being v squared divided by r, and the centripetal acceleration, the centripetal force will be mass times the centripetal acceleration, which equals mv squared divided by r. I've used lowercase, but uppercase is fine. Okay, so what I'm going to do now is going to link it back to the period, because sometimes you're not given the radius, you're given the actual time it takes in terms of the period. So just deriving it here, A equals V squared divided by R. Okay, that's pretty straightforward from the previous slide. Okay, but what happens instead if you don't have R, you have the period instead. Okay, so velocity, of course, equals distance over time, and in the circle that's going to be 2 pi divided by t. That should really be capital T, capital D. Okay, so we then, all we do is we substitute b squared into there. Okay, so it's going to be 2 pi r divided by t all squared divided by r. Okay, so all we've done here, maybe a little bit of that r. All we've done here is substituted v into the equation, where v equals 2 pi r over t. So that means that will equal 4 pi squared r squared divided by t squared times 1 over r. Remember, this is going to be equal to 1 over r, and then we'll basically cancelling out things. That cancels out, one of those cancels out, so it will be, acceleration will be 4 pi squared r divided by t squared. Okay, and because we already know from Newton's second law, force equals mass times acceleration, this means that we're basically substituting it in to the equation, so it will become force will equal 4 pi squared m r divided by t squared. There we go. Okay, a little bit better there with r. Okay, so here's some examples that we're going to now work through. So example 1, a 3 kilogram rock swings in a circle of a radius of 5 meters. If the constant speed is 8 meters per second, what is the centripetal acceleration? So let's pause the video now, and then we will go through it in about 5 seconds and see if you're on the ball. Right, so from our equations, we already know that acceleration equals v squared divided by r. Okay, so the mass we know is 3 kilograms, r is 5 meters, and v is 8 meters per second. So therefore the acceleration, centripetal acceleration, is going to be 8 squared divided by 5, 12.8 meters per second. Okay, and that's your answer. And the force will be mass times acceleration, so 3 times 12.8, and it's going to be 38.4 newtons. But you can also use this equation here because that's identical. Right, next question. Example 2. A skater moves with 15 meters per second in a radius of 30 meters. The ice exerts a central force of 450 newtons, or centripetal force of 450 newtons. What is the mass of the skater? Again, pausing the video now, and come back in 5 seconds, and we'll go through the answer. Right, so draw and label a sketch would be very useful for this. So you've got your skater going around the circle. There's a centripetal force of 490 newtons, radius of 30 meters, and a constant velocity around that circle of 15 meters per second. So force equals mass times velocity squared divided by r. Mass equals this force times r divided by v squared by rearrangement. Therefore mass equals 490 newtons times 30 newtons divided by 15 all squared, which gives you the answer of 60 kilograms. Next question. The wall exerts a 60 Newton force on an 80 kilogram person moving at 4 meters per second on a circular platform. What is the radius of the circular path? So there's a little sketch diagram I've also put there. So pause the video now and come back in a few seconds and we'll go through the answer. Okay, so the centripetal force is going to be 600 newtons. Okay, that's what the wall is exerting on the man. And from Newton's second law, the force will equal m times v squared divided by r. Rearrange, get r equals mv squared over f. So therefore, it'll be 80 times 4 divided by 600 newtons, giving a final answer of 2.13 meters. Okay, so this is just going to be the final slide, and it's kind of just a summary of the different equations that you are required to know for this unit, or this little section, and that's the end of mechanics.